In part 1 of Lecture 1, we will discuss what is an operating system. An operating system defines a computer as much as any other component other than the processor, maybe even more than the processor. After all, when you go to buy a new computer, you want one that runs Windows, or maybe the Macintosh operating system, or perhaps even Linux. That's because the operating system is an interface between the user or application software and the hardware. The software has to conform to the operating system's system calls as much as it does to the processor's instruction set. To most people, the operating system is the user interface, whether it's the command prompt, or Windows Start button, or the prompt that you get on a Linux system. People view the operating system as the commands that they use to create, edit, and copy files, or the menus on the screen, or the choice of hotkeys, or whether or not they can delete a file by dragging its icon over to the garbage can. In reality, there is much more to an operating system than what the end user sees. The operating system is responsible for determining how and when to read characters from the keyboard, how to display data on the screen, how to read and write files on a disk drive, and so on. It does these things the way that it does to make it as easy for the users as possible, while ensuring that the computer's resources are used as efficiently and fairly as possible by all the computer's users. A computer system is a little bit like an onion. There are many layers, with the users being the outermost layer, and the computer's hardware being the innermost layer. In between sits several layers, and each of these serve as an interface between the layers on either side. The user's software application serves as an interface between the user and the computer. The operating system serves as an interface between the application and the computer. We could probably add a few more layers if we wished. The computer's microcode, for example. The operating system also manages the computer's resources. Each of these can be used by only one user or application program at a time. For example, the processor, or one core within a multi-core processor, can be shared by more than one user, but only one can use it at any given instance. While memory can be shared, a given byte of memory is usually used by only one user. That means we need to divide memory in an equitable fashion, guaranteeing that each user's needs are met without their programs trespassing into each other's memory. Every user will have files, each of which are stored on disk. Some files they may be able to share, but only one of them can write in a file at a time, or the integrity of the data in the file will be compromised. We need to make sure that a user can keep his or her files private when he or she wishes, and share them when they choose to do so. This means we need to be able to allocate space on the disk for these files as well. Users will probably want and need exclusive use of the input-output devices that their programs use. All of these resources need to be available to users when they need them, and at the same time, we need to make them available to other users. In this way, an operating system is like the reserve desk at the library. The resources to which users need ready access have to be protected, and we have to ensure that the rules that guarantees everyone's access are enforced. The operating system has to act as a master traffic cop. Since everyone can't have the CPU at the same time, it has to determine who gets it next and it needs to do this in a fair manner that guarantees that no job waits too long and that as many jobs as possible get their turns in the CPU per second or per minute or per hour. Also, every program running on the computer needs some portion of the available memory. Every program has some minimum requirement, some minimum amount of memory that it cannot run without. At the same time, no program can encroach on any other program's memory space. If they do, they all run the risk of having their data compromised. Most programs will make use of disk storage at one point or another in execution, and only one program can read or write on a given disk at a time. Don't forget, on some systems, only one disk operation can go on at a time if they are all connected to the same controller, and that controller only allows one disk operation at a time. Lastly, they all need input and output, and if they are sharing a printer or some other input-output device, they need to coordinate who gets it first, who gets it second, and so on. Remember, this is all about making certain that the computer's resources are shared fairly by the jobs who have legitimate access to them, and only to the data to which they have rightful access. Silberschatz and Galvin talk about an operating system being easier to define by what it does than by what it is. And they are probably right. An operating system does all the low-level stuff that programmers and end users don't want to have to worry about. And it also does all the necessary unpleasant tasks that ensure that everybody has the fair chance to use the processor and the computer's other resources. The operating system deals with all the same details of displaying output on the screen, writing files in whatever free space is available on disk, and making it look to the user like one contiguous file. But it is just as important that the operating system maximizes its performance. And that means that we have to determine what the performance goals are. I think that most people would view these as maximizing the user's convenience while making the computer's operations as efficient overall as possible. The operating system is first and foremost an interface between users or their applications and the computer's own hardware. That means that the features available in an operating system depend very heavily on what can be supported by the hardware. For example, most modern computer systems use virtual memory, a little trick where the disk drive is used as an extension of the computer's main memory. This only works if the computer's memory management system can support the data structures that virtual memory depends upon. We'll talk much more about this later in the course. Similarly, it was not an accident that Windows version 3 required a 386 processor, despite the fact that it was a 16-bit operating system. Microsoft badly wanted the operating system to be able to run more than one DOS program at a time, and this required abilities that the 386 processor had, that the 286 processor didn't. This is why Bill Gates referred to the 286 processor as brain damaged. Just as the computer's architecture determines many aspects of the operating system's design, the reverse is true as well. Processor designers frequently include features that will support operating system enhancements. For example, Intel's brain-damaged processor, the 286, was deliberately designed so that it could be used in multitasking computer systems, where more than one program could run without interfering with each other. Gates' comment aside, it would have been a great idea if DOS had not become as popular as it was in 1985.